Welcome, everybody. We are very pleased today to welcome a joint talk by Jon Chaika from Utah University and Barak Weiss from Tel Aviv University, and they will speak about the Horocycle flow on the moduli space of translation surfaces. It will be a registered talk. The talk should come. So I guess the talk should begin soon. It's a pre-registered talk. And the assistant of the session should probably help us to begin the talk. There is a technical issue. So we just have to be patient. We try to. We cannot begin a math discussion because we don't know how long we have to wait. Okay. Just a minute. I didn't plan to say a lot about Horocycle flows or anything else.
which could be, say, SLNR, group of n by n matrices of determinant 1. There's a lattice, which means a discrete.
Hi, everyone. Welcome. So before we begin, I would like to say thank you to the Academy of Sciences and the Math Department of the University of Bologna. And so it is my honor to introduce Jon Chaika from the University of Utah and Barak Weiss from the University of Tel Aviv. They will give us their joint ICM lecture on the Horocycle flow on the moduli spaces.
Thank you very much for coming. Thank you, Florent, for introducing us. Thanks a lot to the people here in Bologna. It's been a great conference and a lovely place to be. And we thank you for inviting us to give this virtual ICM talk here. And I also want to thank our colleague, our joint co-author on this project, which is John Smiley. And so I want to thank him. And I also want to thank the organizers of the ICM for inviting us to give this lecture. And we also would like to acknowledge and point out that we're here feeling with our hearts, thinking about the people in the Ukraine. We completely did not expect these barbaric events to happen, and we wish we could be in more expected circumstances giving this lecture in front of the expected audience. But nevertheless, since it did happen, this is we're very happy to be here with you to give our talk. Okay, so I'll be giving the first half of the lecture. Second half of the lecture will be given by John. The lecture is being recorded, but we would be very happy if you ask questions. And please do, as usual. And let me know if things are not working well for you. So this is a talk about a situation in which one would like to be able to describe all points of a dynamical system, as we've seen during the school. So typically in dynamical systems, you have results telling you what happens for a typical point, or for almost every point. But in some situations, you can have a theorem that tells you what happens for every point. And that's very rare, but when it does happen, it's a much more powerful result, has lots of applications in other fields other than dynamical systems, and it's extremely interesting. And the paradigm for this kind of results are results in homogeneous dynamics that go under the name of Ratner's theorem. So I want to quickly go over Ratner's theorems, which I'm stating in a very special case, just for this lecture. It's not so important that you understand all the details here. So there's a big group G, which could be, say, SLNR, group of n by n matrices of determinant 1. There's a lattice, which means a discrete group of finite covolume in G. And there is an embedding of a copy of SL2R in G acting on this quotient by left translations. And inside SL2R, there's this one parameter subgroup U sub S, which we've seen during the lectures, and this is giving rise to a flow, and this is called a unipotent flow. And Ratner's results, the first one is called the Ratner measure classification theorem, and it gives you a complete description of all the ergodic invariant measures for this action. All of these measures come about by certain intermediate groups, L. So L is a closed subgroup which contains U, could be equal to U, is contained in G, could be equal to G, or it could be some group strictly in between. Each one of these groups might have a closed orbit. That orbit might carry a finite measure. And if so, you get a measure. And this class of measures is the measures that come up in the measure classification. And they have a description in terms of the Haar measure on L, which I don't want to go into. The second result is called Ratner's orbit closure theorem. And it tells you that all the orbits, if you look at their closures, you get something very nice. You get a closed orbit for some group. In particular, this is a manifold. In particular, these manifolds also carry the measures that appear in the first statement. So the takeaway, it's not so important that you get all the technical details, but the takeaway is there's kind of a reduction from dynamical systems, where we often have orbits which are very, very complicated. Their closures might be fractal sets. They may be very chaotic. But in this particular situation, there's a reduction from dynamical systems to algebra. All the measures come from some very, very restricted algebraic constructions, and they're very nice. The orbit closures are nice manifolds, which is not at all the typical case in dynamics. This theorem is the more striking one, perhaps, for people who are not experts. The previous theorem about the measure classification was proved first, and it's the more powerful one, and it's the one driving these kinds of results. You often first prove a measure classification, and then you use that to obtain an orbit closure classification. A third theorem is called the genericity theorem. It's about the existence of generic points. And a point X is called generic for a flow and a measure if, when you average along the orbit of the point, the averages converge to a certain measure. Yes, John? Oh, thank you. And so that's the definition of a generic point. So if formula 1 that you're seeing over here is valid, then X is called generic for the measure M. And Ratner's genericity result says that every orbit is generic. All points are generic for this dynamical system, which again is very far from being the case in a typical dynamical system. And not only is every point generic, when you're given the point, you can often figure out exactly the measure that it's generic for, very explicitly. And it's, of course, the measures appearing in the previous result. Questions about Ratner's results? These are, okay. So there have been analogs of these types of theorems in the world of translation surfaces. So translation surfaces, many of you know, they appear many, many places in mathematics, and they involve a kind of a space such that the individual points in the space are themselves surfaces. So on these surfaces, we have an individual topological object and a dynamical system, but the entire space is a space of such objects. And on this space, there's an action of SL2R, which will now be denoted by the group G. And we're interested in the dynamics of the group G acting on the collection of translation surfaces because it helps us understand the dynamics on individual translation surfaces. This is the beauty of this field, of this topic. So here's a picture of a translation surface. You take, in this case, 2 polygons, and they're both hexagons. The hexagon on the right is convex. The hexagon on the left is not convex. And the sides have colors, and there's pairs of sides of equal length and parallel, and you should consider them to be glued to each other by translation. So the yellow edge on the left of the right-hand polygon is attached to the one on the right. The attaching map is just a translation. That's a translation surface. And the space of all translation surfaces in which you fix the topology, namely, you fix the genus of the surface, you fix what are called singular points, which I'll describe in a second, their number, their orders. There's a space of all such objects, which is the parameter space on which SL2R will act, okay? So what are these singular points? As you see here the corners of these polygons. Everywhere except for the corners, there's a nice natural flat picture that comes from the polygon. So if I'm here, there's a neighborhood which exactly looks like a neighborhood in the plane because this is a polygon, it's part of the plane. If I'm here, which means I'm here because these 2 lines are identified by a translation, there's also a similar neighborhood. I can draw it in this way. And again, it looks just like a piece of the Euclidean plane. When I say just like, I mean not just topologically, but also geometrically. I can make geometric measurements like area, angle, distance from these pictures. There's an exceptional point here at the corner. And if I go around it, what I find is, first of all, that it's identified with other points. So you see that this point is identified to this point because the green lines are identified. And if I keep going around it, I'm actually finding more and more of these identifications. And this ends up being a point where the geometry is different. It's flat, but it has a cone angle, which is an integer multiple of 2 pi. In this case, 4 pi. And in this case, there are 2 such points in this example. Okay, so that's an example of a translation surface. And the collection of all translation surfaces can be parameterized by the sides of these polygons, like these. If each one of these sides has a length, it has a direction. If I know all the directions and all the lengths of these sides, I can reconstruct the geometry of the surface. Locally, what I need to know in order to, locally meaning locally in the space of translation surfaces, what I need to know in order to understand the surface is to know the length and direction of all of these edges. And this gives me the length and direction of all so-called saddle connections. A saddle connection is some line like this line here, joining a singular point to another singular point, or perhaps the same one. This is one possible saddle connection. Saddle connections might go through the picture many, many times. Like maybe this might be another saddle connection. Some segment that looks like that, etc. So these are saddle connections, and if you know all the lengths and directions of the saddle connections, you know exactly what the surface is like. And this is a way of understanding the local geometry of the space of translation surfaces. If you know the lengths and directions of saddle connections, you know the surface. These are called period coordinates. Sorry. Horocycle flow, the flow that we care about, is given by the action of these upper triangular unipotent groups that we saw before on the space of translation surfaces. And the action looks like this. Here's a simple translation surface made of one hexagon. And when we apply the map, we're just applying the linear action of SL2R on the plane to change the polygon. When the polygon changes, so does the translation surface. So this is a before and after picture. Polygon on the left, sheared by the Horocycle flow. This is a new translation surface. If I keep going, it shears further. If I keep going, it shears even further. But in terms of the underlying geometry, I might apply a very large matrix, get a new surface with exactly the same geometry as I had before. So even though in these pictures, it looks like the dynamics is moving things away very far and not doing anything, actually the dynamics is very, very interesting. Points could come back close to themselves. Orbits could be complicated. We have an interesting dynamical system. I'm going to state the results of Eskin, Mirzakhani, and Mohammadi, which were a very big deal about 10 years ago, I think, more or less, or 8 or whatever, and they are the background for our work. Let's take P to be the upper triangular group in SL2R. So this is not the group we've been considering before. U, it's the group we've been considering before, and an extra one parameter group of diagonal matrices, and they generate the group. And Eskin Mirzakhani classified the measures for this action on the space of translation surfaces. Eskin Mirzakhani and Mohammadi classified the orbital closures in analogy with what Ratner did. So here are the statements, which I'm not giving you in precise form. The measure classification theorem very briefly says all the measures are geometrically nice. I'm not defining what nice means, but I'll give you an example. So here's an example of a collection of surfaces with a special symmetry. Think of surfaces made of 2 hexagons glued to each other. The gluing is just as before. The topology is just as before, but there's a special feature. The 2 hexagons are exactly the same. So you're seeing 2 identical isometric hexagons. And surfaces that have this extra symmetry are special. And if you apply SL2R, the symmetry persists. If you apply any element of SL2R, the symmetry persists. And the collection of all such surfaces is an example of a subspace of the space of all translation surfaces, which is nice and geometrical. and it carries a nice measure, and all the measures, as Eskin and Mirzakhani proved, this is a very difficult and deep theorem, have this feature. Technically speaking, the feature is that in the period coordinates that I mentioned before, there are equations describing this locus, and the equations are linear. So in this case, it's very simple. This edge, say, I'm sorry. This edge here is identified to this edge. So they have to be of the same length because they're identified, but it's also exactly has the same direction and the same length as this edge, which is not the same. Topologically, it's not the same edge. So this is giving us an equation on the saddle connection lengths and directions. It's an identity between two saddle connections that are different. If similarly, you can make linear equations between the lengths or the x and y coordinates of different saddle connections, and that'll give you an example of these kinds of equations that cut out these loci. The next theorem, sorry. The next theorem is the orbit closure theorem. The orbit closure theorem, just as in the Ratner's case, says that all the orbit closures are nice. Nice again means they're nice manifolds cut out as in the example that I gave before. And they also prove a genericity result. All orbits are generic for some measure. But here, the group that's acting is this group P. It's a two-dimensional group. So you average using two parameters, T and S. You average over T and S. And if you do that, every orbit becomes generic. So these are the results of Eskin, Mirzakhani, and Mohammadi. And you might ask, which is what our work is about, what happens if you work with the Horocycle flow, the action of U? Now, if it hadn't been for Eskin, Mirzakhani, and Mohammadi, probably no one would have dared to ask this kind of a question because it seems very far-fetched that a dynamical system of this kind of geometric type should exhibit anything like Ratner's results. Ratner's theorems were in very, very special algebraic situations. And indeed, that's what we proved. So we're going to give you theorems which say that the analog of Eskin, Mirzakhani, and Eskin, Mirzakhani, Mohammadi fails for this one parameter group. Namely, to showcase things, I'm only going to talk about the situation of surfaces in H11. H11 means genus 2, two singular points, just like the pictures that you've seen before. And first theorem that I want to mention is that you can have trajectories for which, when you take the average along an orbit of a function, you don't converge. If you don't converge for some function, you can't be generic, because generic means that you have to converge to some average given by a measure. So certain trajectories, the averages just don't converge, which does not happen in homogeneous dynamics. You could be, there's a technical result which is maybe not so impressive looking, but it's very, very important for us. You might be generic for a measure, but actually not in the support of the measure. So I'll give a picture explaining that and then go back to the statement. So imagine that there's a nice set here which supports a nice invariant measure, but you have an orbit which starts here, somewhere else, and starts moving closer and closer to this set. If you average along the orbit, since it's drifting towards the set, it could be generic for the measure living on that set without actually being inside. In principle, this happens in dynamical systems. We show that such things also happen in our Horocycle flow, in the geometric situation. So X is not in the support of the measure, even though it's generic for that measure. We also prove, and maybe this is the most striking result, but it's this is the most striking one, is that you could have orbit closures whose Hausdorff dimension is not an integer. So they're certainly far from being manifolds. So these are the results. Now I'll pass the, sorry, one more thing to say about this last example. This example, which has a non-integer Hausdorff dimension, is part of a nested collection, uncountably many collected orbit closures, all of which have this property. One is containing another, containing another, containing another, uncountably many, one parameter's worth, and they all have Hausdorff dimension, which is not an integer. So now I'm going to pass it on to Jon. He's going to tell you more.
Thank you, Barak. I'm going to tell a little bit about how our proofs work, some of the ideas that go into them. And as with Barak's talk, as with Barak's part, please feel free to ask questions. Okay, so where are we going to get started? We're going to just start with how we come up with our strange sort of points. And it relies on a definition. So this definition is called a tremor. It relies on a definition called a tremor. And it requires a straight line flow invariant measure on a translation surface. So this is something that appeared for a moment in Barak's part of the talk, but since it's plays such a key role, let's focus in on it a little bit more. And straight line and translation surfaces have lots of such flows. They have one parameter families of such flows, one for each direction. Okay, so what is a translation surface? A translation surface has this special family of charts, which is translations away from these cone points, which Barak talked about. And this is in fact the picture Barak considered. And so because our transition functions are translations, angles are preserved by translations. So flowing in the vertical direction is something that's preserved as you move across charts. And so I want to show you a picture is often worth 1,000 words. So I want to show a picture of this. So we're starting here at the bottom and we're moving upwards along the dotted line. And we just keep moving. Now we run into a problem where we're leaving our chart. Everything was happy and wonderful in our chart. That wasn't special to our situation, but now we're leaving our chart. But we're a translation, so we're still traveling in the same direction as we go. So this gives us really a flow on the surface itself, not on its unit tangent bundle. Okay, and you keep going up to the top of red, and then you'll go and start moving on the other side. Okay, so this is what a translation flow is in a particular direction, the direction I showed. Now, for those of you who are careful, you might wonder what's happening at these special cone points where your transition charts are not translation. Well, the flow isn't defined there. But that's a measure zero set, the set of points that orbit into these given in a fixed direction. Okay, so we still have a perfectly wonderful, measurable dynamical system. And it's very nice, it preserves a Lebesgue measure. Okay, and so there's always going to be a nice invariant measure for it. The measure coming from the area on the surface, and the object I'm just going to be describing, this tremor, is just the Horocycle flow in that situation. So this is a generalization of the Horocycle flow, which we will use to understand the Horocycle flow in some special cases. All right. Okay, so first, the bad news. The bad news is that usually we don't have what I will call interesting tremors, tremors that are different from the Horocycle flow. And this is by a wonderful, depending on the situation you're working in, it's by seminal results, either independently of Mazur and Veach, or by Kirchhoff, Mazur, and Smiley working together, that the flow is usually uniquely ergodic with respect to Lebesgue measure. Usually there are no candidates for so-called, for what I will call interesting tremors. You're only going to produce the Horocycle flow. Okay, bad news? Good news. Sometimes in exceptional situations, there are these interesting measures. And moreover, these measures will be fully supported. They'll see all of the surface. Okay, and that's sort of the setting we will be considering the tremors of these fully supported measures. Even though I won't be able to draw you pictures of them, I will draw you pictures of invariant measures that are not fully supported, and that'll hopefully help suggest what's going on. Okay, so tremors are generalizations of translation flows. So I'm sorry, Horocycle flows. So I want to talk about Horocycle flow, the Horocycle flow first, and I want to talk about it in period coordinates. because it's giving us local coordinates on the space of translation surfaces to define what's locally going on in the Horocycle flow. And we will follow this pattern with the tremor. It's enough to define what's happening in these period coordinates locally. Okay, and it's very nice here. So you can look at the holonomy. You can integrate one of these saddle connections, one of the sides of these. This translation surface has it that its period coordinates are given by the vectors that describe these sides. So I can just integrate these one side with respect to dx, one of these special sides that's giving me my local coordinates, and I can integrate it with respect to dy, and I get an ordered pair. And that's the setting for which the coordinates I'm writing down appear on the next slide. Okay, so you have the integral, gamma is one of the colored sides in the picture I showed you before, maybe the yellow one. And you integrate it with respect to dx, you integrate it with respect to dy. This is a vector that describes it, which is one of the, in this case, it looks like 6, but secretly there's only 5 that matter, vectors that describe the local coordinates at this space. And I'm going to describe what's happening locally with the Horocycle flow in that form. Okay, and so our new surface, I need to tell you what it is in the coordinate that corresponded to gamma. How is it going to change? You're going to take the y coordinate, you're going to multiply it by s and add that toward the x coordinate, and you're going to leave the y coordinate unchanged. That's what it does. This is just how the matrix 1s01 acts on a vector AB. So it's no surprise, and that's how it's connected to this U sub s, this Horocycle flow that Barak defined earlier. It's just its linear action. Okay, now our Horocycle flow preserves horizontal directions, and it acts as isometries on each horizontal line. So secretly, the translation flow in the horizontal direction, not any other direction, just the horizontal direction on my translation surface after I perform the Horocycle flow and before are isomorphic to each other. Okay, and that's just because it acts as an isometry on each horizontal line. Okay. Now, okay, so I want to generalize this, and I already told you how I'm going to generalize it. I'm going to generalize it using dynamical things that come from the straight line flow. Okay. So if we have a horizontal flow invariant measure, we can disintegrate it along vertical lines, and we get an object called a transverse measure. If you do this with respect to Lebesgue, this transverse measure is just dy. And so suggestively, for the fact that this is the version of dy for what some other measure sees the world as being, we'll put the mu underneath it. So that suggests this terminology. Okay. Using such a transverse measure, we are now going to define a tremor. Okay. And so the formula is very similar. So here we're showing, on this line here, we're showing what's happening for the Horocycle flow. And on this line here, we're showing what happens for the tremor. Okay. And so what's the difference? The difference is, well, my base coordinate is the same. So if I set s equal to 0, these both agree, because I want it to be a flow starting from the same point. The coordinates better be the same at the beginning. But they're allowed to change afterwards. So in one case, I move by what dy says gamma is equal to. And in the other case, I move by what this other transverse measure says the length of gamma is, this dy sub mu. So the difference, the only difference between these is one of them they're dy and one of them is dy sub mu. And the only difference is in how quickly it changes the horizontal direction. Right? Now, so the horizontal direction is still being changed by isometries. It's still an isometry on horizontal sides. And so it still preserves horizontal, it sends horizontal lines to horizontal lines. So it still sends my flow in a given direction to the flow on the given direction again. And this is going to be a very useful thing because we wouldn't want to change our horizontal flow invariant measure because then we sort of wouldn't know how to continue going. But the point is the horizontal flow invariant measures are the same because we're preserving horizontal lines. Right? And that's where the horizontal flow is happening. So now I'm going to give you a picture of a tremor in a case where I can actually draw pictures, which is not the case where theorems usually refer to. It's going to be in the situation where there's a measure that's absolutely continuous with respect to Lebesgue, but not mutually absolutely continuous. It's only supported on a subsurface. And the pictures Barak was showing at the beginning are great for this, because here on the left-hand side, we've got a surface that's only glued to the right-hand side by horizontal segments. So for the infinitely defined horizontal lines, which won't be on the bottom because those run into cone points, and they won't be on the top because those run into cone points, you will only stay on one side or the other, okay? So there's a horizontal flow invariant measure on the left-hand side, which is just Lebesgue on the left-hand side. And there's one on the right-hand side, which is just Lebesgue on the right-hand side. And so I'm going to do the tremor with respect to one of these, the one that's on the left-hand side, Lebesgue on the left-hand side, okay? And so if you remember Barak's picture from before with this tall hexagon, with yellow, red, and black sides, the whole hexagon was being tilted. But here, I'm doing the tremor that's only living on the left-hand side. So this measure that I was defining before, this dy sub mu, it's going to be 0 for any saddle connection that's on the right-hand side. This measure right here in, this measure that's in blue here, it's going to be 0 whenever gamma is only on the right-hand side, okay? But it's not going to be 0 if gamma intersects the left-hand side, or at least that has a chance not to be. And so let's see what happens. So our saddle connections that are on the left-hand side, well, it just is Lebesgue on the left-hand side. So they're going to move as if this was the Horocycle flow. And the guys on the right-hand side get 0 transverse measure because the measure doesn't see the right-hand side at all. And so this is what happens from one unit of time of tremor. At the next unit, it tilts further and it tilts further. Okay, so this is what a tremor does. So at this stage, I'm going to be moving towards proving that there's a point whose Horocycle orbit is not generic is generic for a measure, but it's not in the support of that measure. This cartoon that Barak was doing of the thing circling into a set that it's not lying on. And this serves as a good way of seeing a couple of our arguments. So that's why we're going to focus in on this. And it's a sign of sort of how things are going. Oh, it's also a sign that things are going wrong, that this setup of really good rigidity doesn't hold here. Okay, so I want to talk about important properties of tremors for me. They're defined for surfaces that emit horizontally invariant measures other than Lebesgue. They depend continuously on the horizontal invariant measure, and it defines a flow. This comes from the fact that it preserves the horizontal flow as a measurable and topological object. The fact that this measure mu makes sense after you apply the tremor for time t, and so you're able to apply it for time s in the future. The fact that this expression on the right-hand side here makes sense comes from this isomorphism. Okay? And lastly, it commutes with Horocycle flow. And why does it commute with Horocycle flow? It's just a function of how this looks like in coordinates. And I'm just adding different numbers into the x coordinate, and addition commutes. That's really all that's going on with it to commute. And then to say where we're headed, let me say this. So kind of a key idea that's going on is our weird objects largely come from the Horocycle orbit of a tremor. Thank you. The Horocycle orbit of a tremor of a point. These are our weird Horocycle orbits. So these are the Horocycle orbits. So S is varying. But the way we understand these is we look at a usual Horocycle orbit, U sub S of X, and we apply the tremor for a fixed amount of time to that Horocycle orbit. So this is sort of the key idea of the proof. We want to understand the left-hand side, and to do that, we work with the right-hand side. Okay, so where is the setting we're working in? We're working in this example of one of these loci that Eskin Mirzakhani and Eskin Mirzakhani Mohammadi were talking about, where you have two tori, which in this picture are represented by hexagons, which are identical and that are glued along the slit. Okay, so this is the object we're going to start with. And this is a collection that's, as Barak said, closed in invariant set, SL2R invariant set in H11, and it's 5-dimensional. And it's a very special set. It's a cover, in fact, a 4-fold cover of the space of tori with 2 marked points. So it can admit study by special methods. So we're looking for our interesting phenomenon in a special situation in a couple of ways, where we're starting from as a special situation, and also we're using this non-unique ergodicity that's special. Okay, so we need situations where we have minimal and not uniquely ergodic flows on these objects. And these were proven by a number of people, Veach, Katok, Stoypin, Macer and Smiley, and suffice it to say there are many examples of these, and there's sort of a good understanding of these examples. They've been much studied. And so what's the moral for this talk? The moral is we get interesting tremors. Okay, we've got these interesting tremors that we care about. Okay, and so these interesting tremors, I want to say a little bit about this. Because of the symmetry in this locus, you can find out that any interesting invariant measure you have on it, one that's not Lebesgue, has to be not preserved by the involution of the surface that exchanges the 2 copies. It sends one ergodic measure to the other. So this has an asymmetry to it. And what that asymmetry means is that when I tremor, I'm going to move off this locus. And so connecting us back to what I'm explaining first, this point that's generic for a measure that it's not in the support of, what's going to happen is the asymmetry is going to move us off of this locus, this E4 locus. But as we apply the Horocycle flow, at least in mass, we're going to fall back into it. Okay. All right. Now, how am I going to prove that we're going to fall back into the locus? We're going to use the fact that tremors vary continuously with respect to the measures, and that the measures themselves have sort of a semi-continuity property. When your only invariant measure is Lebesgue, there's a neighborhood about you where all of the surfaces in that small neighborhood, all of their invariant measures are very, very close to Lebesgue. Okay? And so what's the moral of the statement? I now want to state a more mathematical statement that's a moral of the statement. There's an open set of full measure. So you look at all of the non-unique, all of the uniquely ergodic surfaces, all of the surfaces where the horizontal flow is uniquely ergodic, and at each one you can thicken it by a little bit by an open set, so that all of the invariant measures in this open set are extremely close to Lebesgue. And that means that the tremor is going to differ by the Horocycle flow, the tremor coming from Lebesgue, by very, very little, because these measures are very close. So dy sub mu is going to be very close to dy. The numbers you get are very close. It's going to be very close. Okay. All right, so now this is a moment where our perspective plays a key role. If you started outside of this nice open set, so you got tremored off at definite rate from the eigenform locus, from this E4 locus, because you broke the symmetry of the surface, because your ergodic measure gave the 2 tori different weight, you still might land in this open set of full measure. It's open, it has full measure. How could you help but land in it a lot as you push forward according to the Horocycle flow? So if instead you think of Horocycle flowing first, landing in this open set where all of your invariant measures are very, very close to Lebesgue, and then tremoring it, you will have proved that your tremor didn't move very far off of the locus. And in particular, the tremor looked a lot like Lebesgue, so you just moved basically one more step of Horocycle flow. Okay? And so the moral of the story is now, of course, you're very, very close to this E4 locus. And this is going to be the way in which we get a point that didn't start on the E4 locus, because you tremored off of it, and yet it's forced to fall back into it. Okay, now to use ergodic theory to treat this, we're able to quote a work of my 2 co-authors, John Smiley and Barak Weiss, and also Matt Bainbridge, who says that if your horizontal flow is minimal, so even if it's not uniquely ergodic, but if your horizontal flow is minimal, then you equidistribute with respect to this natural measure given by Eskin-Mirzakhani theorem for this locus. So we understand very well the points that equidistribute for this, and there are even points that have interesting tremors. And the moral of this, because this is a measure, the way it plays with open sets is fairly nice. So you have to, your Horocycle orbit, this US orbit of the base point we started with, the base point at E4 we started with, has to spend 100% of its time in this nice open set where the tremors don't push you very much. So the moral is 100% of the time, this inequality holds. You're very, very close to the locus, and you're very, very close to just horocycling flowing one more unit of time. Now, I should say one word about what I mean by 100%. 100% doesn't mean all the time in this talk. What 100% means is if you look at the amount of time where it fails to be true, that goes to a zero proportion of time. So you wait after 10 billion years and you divide by 10 billion years and it's small, but you have to divide by the amount of time and that goes to zero. So 100% doesn't mean all, okay? It just means 100%, okay? Okay, so this part of the talk is about this point that's generic for something that's not in its orbit closure. And what I want you guys to have seen, having been helpful here, is the fact that you commute with the horocycle flow. And to understand the horocycle orbit of the tremor, you instead understand the tremor of the horocycle orbit, and the importance of the fact that tremors vary continuously with respect to the invariant measures. Those were two key things in here. Now, the orbit closure statements are rather technical to prove, but I can still tell you what the orbit closures are, and you can at least start to get a feeling for the role in which tremors play in them. Okay? So I want to look at a subset of the of this E4 locus, which are those surfaces where the horizontal flow is aperiodic. So in particular, these pictures of the two hexagons I drew before, though the horizontal flow there might be aperiodic, even if it's not minimal. It's so long as you're dense on the orbits on the left-hand side are dense on the left-hand side, and orbits on the right-hand side are dense on the right-hand side. Okay, and then I want to consider this object, S sub tau. And what I'm going to do is I'm going to take all of these aperiodic orbits. I'm going to take all of the measures that come from this, and then I'm going to tremor up until some threshold of time, up to some tau threshold of time. And then I'm going to take the closure of that orbit. I'm sorry, I'm going to take the closure of that collection. So the only thing that's going on here is that this tau, the role it's playing is it's giving me the threshold of these tremors. Okay? And we prove that this is an orbit closure for the horocycle flow. Okay? Moreover, we show that these orbits are nested with respect to each other. That is, if I take tau 2 bigger than tau 1, one of these sets, which turns out to be an orbit closure by what we wrote above there, will actually be properly contained in the other one. So these are what the orbit closures are. And the Hausdorff dimension of this object is between 5/2 and 6. It's strictly less than 6, and it's greater than or equal to 5/2. Now, one side of this isn't too hard. It basically boils down to the set of Hausdorff dimension 4.5, where you're adding line segments, where this orbit closure contains line segments along this set of Hausdorff dimension 4.5, and 4.5 plus 1 coming from the line segments is 5.5. The less than 6 is more technical. Now I want to talk about the failure of genericity in general and where this comes from. What this comes from is the fact that these orbits are dense in our space. And so if we have a surface there's a dense set where all of the surfaces in this dense set are generic for the E4 locus. It turns out that being equidistributing according to a measure along a subsequence is a G delta condition. So these are the sets that are big for the bare category theorem. And in particular, I need 2 of these will intersect. So there's a dense G delta that equidistributes for the uniform measure on this E4 locus along a subsequence. The Horocycle flow itself is ergodic, so there's a different dense G delta set where it equidistributes along a subsequence for Lebesgue measure. In this case, a dense G delta full measure. And these two have to intersect in another dense G delta by the Bayer category theorem. At this point, I think I'm out of time. Thank you very much for your attention.
Do you have questions? Sorry, of course, I bring you the mic.
What does it mean for the flow to be aperiodic?
Can you use this microphone to answer after?
Oh. What it means is that the orbit of no point has that its orbit comes back to itself. So it starts and ends at the same point. Thanks for the question.
So you can do this construction in H11, but are there other loci where you can do similar construction? And what do you expect for other invariant measure by the Horocycle flow on other loci?
So I think that this construction is fairly general. What are the tools we need in which for it to run? We need to have a locus where, so let's say something that's completely general. If you have a locus which has a flow on it which is minimal and not uniquely ergodic, and one of the invariant measures define a vector, and the tremor comes from a vector coming from this dy sub mu. If that is not in the tangent space of your orbit closure, then it will be such an example. You tremor with respect to that, and then any weak star limit of the uniform measures on the Horocycle orbit of this tremor point will have that support is contained in the locus you started from, basically for the reasons we explained here. We don't know exactly what those could be in general, because we don't know the Horocycle measures in that situation. But you'll still have this phenomenon where it's any measure that it equidistributes for along a subsequence, it won't be in the support of. Now for Horocycle invariant measures, I don't know. I think that's still widely open and we can't prove anything about sort of new exciting Horocycle invariant measures.
More questions? If not, I want to thank you for this very beautiful lecture. And
okay, we thank all the participants to this online session and the two speakers, Barak Weiss and Jon Chaika, for this wonderful registered talk. Thank you very much.